In machine learning, it's very common to have to deal with statistics. And in this video, we'll particularly look at the concept of an average or mean for a data set, and we'll look at it in probably a new light than you might be used to it. So we are probably pretty familiar with computing an average, also known as a mean. And so just to illustrate an example, suppose we have three friends. These three friends have in their pockets $5, $10, and $15. And if we computed the mean, which our standard way of doing it is to sum the values and divide by the number of values, right? That's the operation we would get. And this would give us $10. Well, $10, what does that mean is the ultimate question. And well, we took dollars and we divided it by people. So this would be $10 per person. And the reason we look at this example is because what this would mean is if we pooled together their money, or they pooled together their money, and then redistributed it, divided it out among the three people, each person would get $10. And that's really the key point behind a mean is it is the numerical value represents what all the values would be if we redistributed these values. You can see if this person gave $5 to this person, well, then everybody would have $10. And that's where we focus on the interpretation of that average. Now, suppose a fourth friend brings $15. The new average would be $11.25 per person. But notice how we can compute this mean. So one way would just be to take the 5 plus the 10 plus the 15 plus the new 15 and now divide by 4, right? But what I want you to focus on here is how this can be done alternatively. Well, really what this is this is 1/4 times 5 plus 1/4 times 10, right? Basically just taking 5 over 4, 10 over 4. And then if you notice here, we have two 15s, right? So we could do 15 over 4 plus 15 over 4, but because 2 out of those $4 amounts are 15, we could apply 2/4 to the 15. And this is often how we actually compute averages in statistics. We take the relative frequency, or in our case, it would be a probability. Here, these aren't probabilities, these are known fractions, right? But you compute the average as if they were random components. Well, then these would just represent probabilities. In this case up here, the way we could have written this 5 plus 10 plus 15 is to take 1/3 of 5 plus 1/3 of 10 plus 1/3 of 15. So these coefficients that we see here, these are called the weights, right? These are called weights. And the reason they're called weights is because, well, they represent how much each of those terms weighs in computing that average. Now over here, those weights are not all the same, right? In fact, the number 15, that dollar amount, holds more weight. It holds twice the amount of weight than both 5 and 10. And that makes sense because there are twice as many 15s in that calculation as there are 5s and 10s. Now in statistics, we, instead of calling it an average or mean, we typically refer to this number as the expected value. Expected value, the word expected just means if you were to repeat something many times over and over again, what would be the value that you would come up with? Now again, there's nothing to really repeat here. These are known dollar amounts. There's nothing random going on here. But the idea is the same because in probability, these numerical values that we have, these are the values of the random variables. So if you let's just pretend for a moment that we called these little x's, we called them 5, 10, and 15. And while we shouldn't really call these probabilities, we'll just call them relative frequencies, would be 0.25, 0.25, and 0.5. And you can see that our probability sum to 1. We've accounted for all the values. So to calculate the expected value, we could just say multiply the values times their probabilities and then sum that result together. Okay, well that's all we really do when we're talking about a discrete probability distribution, is we take the value multiplied by its corresponding probability. And this notation here just means for all values of the random variable capital X. Okay, remember capital X is just the keeper, if you will, and the little x is each of the individual values. So X is the set, little x are the elements of the set. Now, if you recall, we had an example where X represented the number of heads in 2 coin tosses. And so we had a fair coin. We tossed this coin twice. We could get 0 heads, so both tails. That happens 25% of the time. We could get 1 head. That happens if you get heads, tails, or tails, heads, either of those sequences. And then the only way to get 2 heads is to get heads, heads, and that occurs 1/4 of the time. So if we want to know what's the expected value and what does it mean, well, the way we typically write the expected value is we write it as E of capital X. There are different notations for this, but we'll use this one here. And that's just going to be the sum of the probabilities, the values times the probabilities. And so that we would have 0 times 0.25 plus 1 times 0.5 plus 2 times 0.25. And if you multiply these together, you will get 1. Okay, well, let's think about what actually happened here. First of all, the units would need to be related to the number of heads. But keep in mind, this is the expected value. So this is an average. So we would expect on average to get 1 head per toss. All right, units. So if we did this average the old-fashioned way, we took 0 plus 1 plus 1 plus 2. The reason I'm doing it that way is because if you think about it, there are 4 outcomes here, and those 4 outcomes have 0 heads, 2 of them have 1 head, one of them has 2 heads, and we divided by 4. Well, that would be, I guess you could call this outcomes. And then this would be the heads. So this would indicate that this average, just computed differently, but it's the same mathematics. This would be 1 head per outcome. Now I'm not going to use the word outcome. I'm going to say per toss. Per 2 tosses, excuse me. Because this is... So on average, and this should make sense, right? Because you are more likely to get 1 head than to get 0 heads and 2 heads. And if you look at this probability distribution or the probability mass function, and you put 0.25 and 0.5 as the probabilities, well then to get 0 heads, 1 head, and 2 heads presents asymmetry, so it would make sense that your average would be right in the center because the balance on either side is exactly the same. So on average, you would expect to get 1 head per 2 tosses. The average number of heads per 2 tosses. So what this means is that if you were to repeat this experiment many times, if you were to toss a coin twice and you recorded the number of heads, and you kept tally of how many times you got 0, 1, or 2 heads, what you would expect to see is that, maybe out of 20 tosses, and this is, randomness may not make it exactly this amount, but let's just say this happened 5 times, this happened 10 times, and this happened 5 times. Well, then if you took and added up the total number of heads that you got, here you got, 0 heads. Here you got a total of 10 heads, and here you got a total of 10 heads. And now you took the fact that you ended up with 20 heads total, divided by the number of times you repeated this experiment. That would be 20 heads in total divided by 20 times of tossing a coin twice. That would be one head per 2 tosses on average. Now, when you're dealing with continuous distributions, we sum infinitely many products. Remember that these point mass functions are no longer point mass functions. We're talking about a density function, and that is what we refer to here as the PDF, which is f of x. Now, some people will call this little p of x, and that's fine too. This is just an alternative. But what we want to emphasize is that the density doesn't output probabilities. It outputs the density. And when you take areas under that probability density function, that's when you get probabilities. So let's take a look at an old example. Buses arrive at a bus stop uniformly between 0 and 10 minutes late. All right, so that means that's a random distribution. So here we've already seen that the density function is 1/10. And so all that means is that the values of x have a uniform distribution of a height of 1/10 between x equals 0 and x equals 10, so that the area under here is 1.00. So it's 100% of all the possible outcomes. The bus will arrive somewhere between 0, it'll arrive either on time or up to 10 minutes late, and there's any number, right? It could be 0.012956 minutes late, and so that we might infer that that's pretty close to 0. So the random variable x is the number of minutes by which the bus is late to the stop. Find the expected value and explain what it means. Well, I don't know about you, but if I'm thinking about this, I might imagine that if it could arrive equally likely anywhere between 0 and 10 minutes on average, I would probably expect the average to be 5. Well, let's see if that's true. So what we're going to do is we're going to, first of all, take x, which in this case, it's literally just x, right? It goes from 0 to 10. So to calculate we can't actually plug in the numerical values for x like we did here, here, and here, because there are infinitely many of them. So symbolically, the way we do that is we say, well, the expected value of x will be the integral across the entire probability distribution. Well, that'll be from 0 to 10. Okay, so that integral will regulate the value of little x, and then it will also regulate the probability density function, like so. And so now what we could do is we could take the integral from 0 to 10 of x times 1/10, which is 1/10 x, dx. So integrate that. That'll give us 1/20 x squared. And now we need to evaluate that from x equals 0 to x equals 10. So we get 1/20 of 10 squared minus 1/20 of 0 squared. And that's going to be 100 divided by 20. And check that out. That is our average time. So on average, the bus is expected to be 5 minutes late. Okay, so that means if you rode the bus many times and you arrived at this bus stop and you recorded how many minutes it's late by, and you did that, say over the course of a year or 2 years, and then you took all of those times that you had there and you computed the average, you should be expecting around 5 to be that average. Will it be exact? Well, no, because the expected value is over infinitely many attempts. Okay, furthermore, as a brief extension, if you don't have the random variable, but you have some function of the random variable, then the expected values of that function of x are computed the exact same ways, but instead of adding the x's, you add the functions of x. So let me give you the example here. Suppose x from the bus arrivals example is cut in half. So what we're saying now is that we know that the bus arrival times were uniformly distributed between 0 and 10, but let's say we cut those arrival times in half. So if x is the random variable, in this case we would just say the expected value, so g of x would equal twice x. I'm sorry, not twice x, half x. It would be half the time, it would be twice as fast. half of x. So to compute the expected value of this function of x, well, we would take the integral still from across the entire distribution from 0 to 10 of 1/10 times 0.5x dx. And not surprisingly, this would just cut that average in half entirely. So that's all we would do if it's just some function of our random variable. Now, finally, one of the things that we'll often need is we'll often have vectors of random variables. So let's just say that you collect data on a person, maybe you get their age and they're 25, and you get their height and maybe they're 65 inches tall, and maybe their weight and maybe they are 145 pounds, and so on. And you collect a bunch of variables and you repeat this many times, right? You repeat this many times on many people. Maybe this is person 1, person 2, person 3. And so you have age, you have height, you have weight, and you store the data in vectors. So it's impractical to try to just extract all of the ages, extract all of the heights. It's probably better just to keep the individual data in vectors. So to compute the expected value of a vector of random variables, not surprisingly, you would just compute the average of all of the ages, store that as the top component of the expected value vector, the expected height, and on down expected weight, etc. And the reason we say that that's going to be an element of RD is this is going to be a D by 1 vector. We'll have D random variables in here, so it's going to be in R.